All right, so in today's quiz we were supposed to relate output voltage with, or output signal with input signal. We can recognize that output signal is from, it's a potential difference across the capacitor. Now, well, the question actually refers for peak values, so you could use either complex analysis or directly impedances. How about if I show, because maybe last time I was doing it with complex analysis, so how about just looking at real analysis? So peak value of the output voltage, oops. We can recognize that peak value of the output voltage is equal to peak value of the current flowing through the capacitor multiplied by impedance of a capacitor, which is related to angular frequency of the signal and capacitance of the capacitor. Now, if I mean the filter will work properly if the impedance of the load on the right hand side is high. So I mean, it would be ideal actually to have it open like we have now in the circuit. However, it would defeat the purpose. We have unfortunately to take all approximations in engineering and just assume that whatever we connected over here will have high impedance, so practically these two elements will share the current, and so the current in these two elements is going to be the same. They are connected in series, therefore, and if they are connected in series, I can relate the peak value of the input voltage with the peak value of the current flowing through that system. So I have to divide peak value of the voltage. I have to divide this by impedance of the combination of resistor and the capacitor. So now remember that impedances don't combine like resistances. And for elements connected in series, impedance of I will have impedance of I need square impedance of the resistor and square impedance of the capacitor, and take square root of it in order to get the current. And now I have to multiply it by 1 over omega c, and I got relation between output signal and the input signal. At this point, actually, even if you do not simplify it, because we could simplify it by bringing it omega c into the, oh, why don't we do that actually? So I can write down that this is 1 over, if I bring this product of angular frequency and capacitance into underneath the square root, I will, this omega c and this omega c will cancel, so I will have square root of 1 plus omega angular frequency, capacitance, and resistance squared, and multiply by the input peak value of the input voltage. From if we obviously this was not a question, so this was the end of the question. However, let's now think, what kind of filter do we have? Is it a high pass filter or low pass filter? Well, we can recognize that when angular frequency becomes large, this proportionality coefficient becomes close to 0. So for high frequencies, gain is close to 0. This filter does not transmit high frequencies. For low frequencies, when omega gets closer and closer to 0, this term disappears and gain becomes close to 1. So the filter which you see over there is obviously a low pass filter. All right. I finished yesterday's lecture with with presentation of another electrical element called a diode. And a diode, let me remind you, that diode is an element which has an isotropic resistance. In result, it easily allows current to flow one way and obstructs current in the other direction. And actually, this fact has a quite important application. I mean, I'm using it even here on this table, because a lot of electronic instruments or electronic devices usually require constant potential differences. However, because Tesla won the argument of how to deliver electricity to our households, it is delivered as an alternating current. So somehow now from this alternating current, from this variable sinusoidal potential difference which we have in our circuits, we have to develop circuits which will convert it into constant voltage, ideally constant voltage, or at least direct. And actually they are constant voltage. Yeah, this piece over here, for example, it's called as an adapter. But really what it is, it's a device which takes a variable potential difference from a socket with root mean square value of 120 volts and peak value of 170 volts, and converts it into a constant potential difference of 12 volts. And this 12 volts runs the equipment. Now, I don't have the adapter. I don't have the adapter for the computer, but computer. Right now I'm running it from the battery, but it also the adapter also converts 120 root mean square value into 20 volts. All right. How about if we now take a look how a rectifier, how to build it using a diode. So let's say that this is a voltage which we get from a certain source. Well, if I connect this source to a diode like that, well, whatever now connect to this, and so let's say that this is the device, or or an instrument which requires that it is powered with a direct current. Well, at least I will get direct current over here. Can you recognize that? Consult with each other. Why are we going to get direct current? Talk to each other. Go ahead. And then somebody maybe will be able to come up with the idea and present in front to the entire class. Let's talk.
That guy just blocked the.
Oh, I see. Would you like to be willing to talk? How about you? You will? Okay. You will?
Sure.
Mm-hmm. All right. How about if we hear an opinion? Yeah, so this would be the current through this device if we didn't have the diode. Yeah, now what will the diode, how the diode is going to affect that current?
When the diode encounters, or when the alternating current encounters the diode, it sees great resistance in one direction and very little resistance in the other.
Right. It has one, and let me remind you when. Yeah, so when potential on this side is higher than potential on this side. Now let's say that that it's the same. I mean, really it is. Yeah? I mean, if this is a resistor, and let's assume that it is. So at this instant over here, we will have highest potential over here, corresponding to this current, determined by the resistance in this direction. So at this instant, potential here is high, potential here is low. At this instant, potential here is equal to potential here. The generator does that. And at this instant over here, potential on this side is lower than potential on that side. Now recognize actually that when the diode is over here, the diode together with this element make a kind of a voltage divider, which means potential over here is somewhere between this one and this one. I mean, particularly if this is a resistor. I mean, usually whatever we connect behaves like a resistor. So although it doesn't have to be true, but if it is a resistor, then definitely potential at this point will be higher than potential at this point and lower than potential at this point, provided that potential here is higher. All right, so if potential here is higher, potential here is lower, the diode is, how the diode is biased?
Forward.
Forward biased, correct. Then the forward bias, its resistance is low, right? So it behaves like a piece of wire. Yeah, so current will flow through this circuit. All right, what will happen now in this instant?
Sees a higher resistance.
Correct. So this time the diode will have higher resistance because now potential here is lower than potential here. So the diode is biased. How is it biased? No, we don't call it high. It will have high resistance, but the diode is reverse biased. Correct. It is reverse biased. It has very high resistance. Ideally, it would have so high resistance that we can consider that it's an open switch. It's disconnected. It's a break in the circuit. What current will flow in the circuit then?
Direct, one way?
Well, no, I mean at that instant.
Oh,
None, correct. The current won't flow. So if the plot over here represented current in the circuit without the diode, with the diode, this is what would be the current. The current will flow only one direction, so we at least got direct current. It's not particularly nice current though, right? Why not? Because what? Well, first of all, well, it's spiky, and another thing is that indeed half of the time there is no current flowing at all. So this type of a circuit would be a poor adapter or poor power supply. Well, however, we can improve it. We can improve it if we put a capacitor over here, and this is indeed a case in which the purpose of a capacitor, I think it's the first time actually that I brought up a capacitor where its purpose is to store charge. Really, in this situation, the purpose of having a capacitor is to store charge. Because now let's see what will happen. Let's try to analyze, and I'm going to show show you how it indeed how it works. I will assemble a circuit and show well, both situations. So when the current now flows, what happens with that charge flowing through the diode? Well, some of this passes by through the to the device which we want to power. And which way the current will flow? Up or down? Down, correct. Well, some of the current will flow over here and charge the capacitor, right? So, and for how long? I mean, it will charge up to this point. Now, well, capacitor is going to be charged, and well, voltage potential at this point will start to drop. Well, capacitor is charged, so capacitor keeps high potential over here. So suddenly the diode becomes reverse biased even before it potential over here drops to 0. Well, but capacitor is so the diode disconnects this part of the circuit practically. It assumes, I mean, it's reverse bias, so its resistance becomes high. It doesn't conduct anymore. Well, so what powers now this device? The capacitor, correct. Now charge from the capacitor cannot go back. Yeah, because diode prevents it. I mean, capacitor keeps the high potential over here because it is charged. So charge now the charge from the top plate tries to go to the lower potential. It cannot go through the diode. Well, it powers this circuit which is connected to the right-hand side. If I can recognize it, I mean, if I consider that this part of the circuit has a certain resistance, I have an RC circuit. Do you see that? Now, so the capacitor will be discharging through, well, think that this resistor. How does it discharge? Along what curve? What is the function which says how it gradually drops? I mean, it gradually discharges, right? Capacitor gradually discharges, but at what rate? Is the rate constant? Or in other words, is the charge on the capacitor now a linear function of time? No. It was exponentially discharging. So it is going to be discharging. Well, how about if I mark it? Yeah, so it is discharging exponentially until potential over here increases to a value that the diode is again forward biased. And when the diode is forward biased, then it takes over that load connected on the right-hand side, and at the same time it is recharging the capacitor. Isn't it neat? Can you see? Is it crystal clear how that how this half-wave rectifier works? Who is still confused about it? Well, no. Let's put it the other. Who understands now crystal clear how the rectifier works? Just Will? Andrew, you don't understand that?
I've heard the one of these before, and it doesn't work out, so I'm not going to claim crystal clear knowledge on this.
Jerry, how about you?
I'm just close, but I'm kind of trying to figure out how the diode ends up going back to being forward biased.
Oh, okay. Yeah, that's great. Yeah, so Jerry understood up to this point, right? All right. So now to the point where potential at this point had the highest value. When potential here had the highest value, the diode was forward biased. It was charging the capacitor and supplying electricity to the load, right? Well, so what was happening with the potential over here? What value of potential did we reach over here? Which one? No, high. eventually high. Yeah, I mean, the diode behaved like a piece of wire, right? So we had high potential over here. Actually, how about if you, let's think that that resistance of the load is infinite. All right? Now, let's say that potential drops over here. How about if we think that at this point, let's say that that potential at this point was 10 volts. So what was potential at this point? Also 10, correct. When it was charging, it was also 10. Now, the cycle continues. Here we have an infinite resistance, and potential here drops to 9. What's potential here? No, 10. Mike, why do you think that it is 10? And you are right.
Because the capacitor takes
Because the capacitor is fully charged. Yeah, the capacitor is still fully charged. It didn't have a chance. It cannot discharge through the diode. The only way it can discharge is through that load. Yeah, so when it gets charged, it's stuck. Yes, why don't you give him that? Yeah.
No, I was just saying, right, when the capacitor could I say when the capacitor reaches its full potential, say at a 10,
Right.
then that other section right there
Yeah,
increases its in value, or would you say that?
Well, that one oscillates. Yeah, this one oscillates over here.
Okay.
So in order for the capacitor to get sufficient charge to create potential of 10 volts on this side, potential of that source had to go to 10 volts.
Mm-hmm.
Yeah, so when it went to 10 volts, it charged the capacitor and created potential of 10 volts on this side.
Okay.
Now, when potential dropped over here, if capacitor has no way to discharge, it will keep potential difference of 10 volts forever. And we will see it. You know, the only way that it can drop potential difference over here is that it has to discharge through the load. Is it clear? Is it crystal clear now, Jerry?
Well, so when the capacitor is completely discharged, then basically it's almost like it's not there, and it just goes back to the whole process again. Is that right?
When capacitor is completely discharged, it's correct.
So
Yeah, but what we are trying to do, we are trying actually to select such capacitance, and we will have to adjust it appropriate to its function. So whatever we will put, what will be the resistance of the load, we'll try to select a capacitor, such a capacitor that it doesn't discharge to 0. Ideally, actually, yeah, because what determines how fast it discharges? Yeah, the symbol for it was tau. It's product of capacitance and resistance. It was the time constant of the circuit, right? We would like to have an infinite time constant, because if we have infinite time constant, we will maintain, the slope over here would be invisible. And we will maintain really constant current rather than, because right now we have a fluctuating direct current. Do you see that? All right, now Tim, I think, somebody noticed actually that we are using only half of the cycle, right? It would be nice actually to use also, so this part is wasted. This part of the time is wasted. Well, we can have a full wave rectifier, which requires 4 diodes. If we assemble diodes in such a way, then we take advantage of both positive potential at this point and negative potential at this point. Now let's see how this works, yeah, because now we will have to trace what happens with the diodes. So let's say that potential over here, that the source produces higher potential here and lower potential here. Yeah, so over here we have the lowest potential. And over there we have the highest potential, which which of the diodes are forward biased and which of the diodes are reverse biased. Well, let's start with this diode. Is this diode forward biased or reverse biased? Forward. How about this one? Reverse. How about this one? Forward, right? Here we have the lowest potential. And this one? Reverse. All right, so now you can think that the circuit, that these two diodes don't exist. They are switched off. Yeah, there are breaks here. And here we have the highest potential, so current is going to flow this way, charge the capacitor, supply energy to the load, and through this diode, go back to the power supply. Do you see that? Who could see that? All right. Now let's see what happens if potential half a cycle later. Potential here is now the lowest. Potential here is the highest. So if potential here is the lowest, which of the two diodes is forward biased? Is this one forward biased? No. This one is, right? How about these? Here we have highest potential. So which of the diodes is forward biased? The top one or the bottom one? Top one is forward biased. This one is reverse biased, right? Here we have the highest potential. Current flows this way through this forward biased diode, charges the capacitor, provides energy to the load, and comes back to the power supply. Yeah, so in this circuit, when potential here is higher than potential here, these two diodes conduct, these don't, and current flows down through the load and charges the capacitor. When potential here is lower than potential there, then these two diodes conduct, and current still flows down. See that? So if I supplement now this plot, how it is going to look like, that whenever we had a negative value, it still works. So it reduces already the fluctuations. All right. Now I wanted to switch to the demonstration. And look at this circuit here. I have already assembled this circuit. Now there's a lot of wires, and actually I assembled two circuits over here. So the one which I'm talking about now is this one. I even misused the diode because it doesn't make sense to take a light emitting diode for this purpose. But light emitting diode will glow whenever current flows through it. So you will recognize when the current flows and when it doesn't flow. And I have here the load resistor. Yeah, so I mean over here it doesn't make much sense at this point, but this is what this represents whatever I want to deliver that electricity. And here I have this capacitor which is going to be charged and discharged, which actually for a moment I will take it out. So it's a situation that we have a circuit containing diode, and this diode allows current to flow to your left. So circuit is like this now. See that? Do you recognize it? All right. And I'll turn on the circuit, yeah, so you can now see it. Right now it operates with frequency of 5 hertz. I mean, I'm not sure if at the back you see that the diode is blinking. Can you see that? Now, by those of you who sit closer, you can see that the diode is blinking. Well, however, because and now with this terminal, I really measure the potential difference across the resistor. So the green line, that green line over here really represents potential difference across the resistor, but because potential difference across the resistor is proportional to current in the resistor, so if I think about different scale, I can, if I multiply, if I divide this plot by resistance of the resistor, I will really have a plot of the current. Yeah, so you can think about it simultaneously as the voltage across the resistor or current through that load resistor. And we can recognize actually that it does not allow current to flow all the time. Actually, there is one more thing. I mean, something which is inconsistent with the well, the background which we analyzed theoretically on the previous slide. Have you noticed that? Look at the time, at the instances when current starts to flow through the resistor. Well, it starts to flow here, right? Potential difference produced by the power supply is already more than 0, right? And it stops, current stops flowing before it reaches 0. Do you see that? Also over here. Yeah, it doesn't flow just as it is forward biased. Because if we look at the plot of current versus voltage for a diode, a typical diode. In forward bias, it looks like that. So just positive forward bias does not really make the diode conductive. I mean, it is conductive, but still has relatively high resistance. A typical diode requires about 0.7 volts forward bias for dropping its resistance practically to 0. And so this is what happens at these instances. Well, over here it is forward biased, but it is less than 0.7. Over here it's about 0.7. Actually, it's even more than 0.7. If we look at the one division is 1. Yeah, so it's close to 1 volt. Yeah, over here at this instant it is almost 1 volt when the diode starts to conduct. All right, now this was a sloppy power supply. Why? Because of those spikes, right? So how to get rid of them? Put the capacitor into the circuit. All right, so I'm now putting the capacitor into the circuit. Oh, and isn't it great? Yeah, we achieved something. Yeah, we made it. We made it better. And actually, I want you also to notice something about the behavior of the diode. Yeah, this is how it works without capacitor. And now, when I put capacitor, so those of you who are close to me could recognize what happened. Oh, and have you noticed the difference?
Yeah, I noticed that it speeds up a little as far as yeah, it's brighter and it flashes.
Well, the frequency, I don't believe that you notice a change in frequency. However, indeed, when I put the capacitor, it's brighter. Now, why it would be brighter? Anybody has an idea? If not, I can explain it. Okay, give him the microphone. Why do you think it's brighter?
Because there's more current flowing through it longer?
It's more current flowing through the diode and when it is forward biased. And why more current is flowing through that diode? Because it's true. I mean, this is a very good conclusion. More current flows when we have a capacitor. Well, because now the current flowing through the diode not only powers the load resistor, but it charges the capacitor for that missing part. Do you see that? If I remove the capacitor, it only powers the load resistor. With capacitor, it powers the load resistors and at the same time recharges the capacitor. And that extra power delivered by the power supply due to higher current is stored in the capacitor as electrical energy and is used for that missing part of the cycle. All right, now let's actually see what will happen if we change the frequency. So, because right now it operates at 5 hertz. Oh, or maybe not. Before that, I'll remove the load. Yeah, so I take out the resistor. And what do you see now? Well, actually, right now current is not flowing because there's no resistor, right? However, the green line still shows what is the potential difference produced by our power supply. Yeah, this is potential difference where the resistor was in place. So really, this is potential difference right now across the capacitor. And what can we see here? It's constant, right? It's ideal, right? Now, I'll change a resistor because I mean here I have a certain resistor and I'll put another resistor. Great. Yeah, now that our power supplies powers another load resistor. And what can you see it? Or maybe I did something wrong. It looks like I did something wrong, right? How about if I remove the capacitor? If I remove the capacitor, I see that, well, we have those spikes. Yeah? So now I put the capacitor. And we are getting a really constant voltage power supply. See that? Well, what did I do? Why it works? Why does it work with this resistor and doesn't work with this one? Yeah, because right now we have direct but fluctuating. Over here, I had direct and constant. Well, it was because this load resistor had higher resistance. So the time constant for that RC circuit now was so long that we didn't notice that drop of potential. So really this power supply was designed to power this resistor, not that one with direct current. You will have to be careful when you will be playing with electronic circuits and building things that you always have to recognize what are you going to use it for. And actually, I mean, even for this resistor, it would work much better if the frequency were higher. So how about why don't we take a look what will happen if I change the frequency? Let's say it's 10. Let's make it 50. So it is frequency coming out from the power outlets. Well, we see that the fluctuations are much smaller, right? So if the frequency is higher, actually that time constant can be worse than if we power it at a lower frequency. All right. Let's now go back to something else. Now I would like to talk about another device which is called a transistor. Actually, I will talk about two transistors. One transistor is called a bipolar transistor, and transistor is an element which has three sides. The names of bipolar transistors terminals are emitter, base, and collector. Transistors actually are made from three regions with different type of conductivity. So we take a semiconductor material and dope it in such a way that we have N-type, P-type, and N-type, or P-type, N-type, and P-type. And depending on this, which one we have, we call the transistor PNP transistor or NPN transistor. So for example, this transistor over here, which is this, for which we have the diagram over there, is an NPN transistor. Now, transistor actually also works like a kind of resistor which is controlled with current. So if I this one is base, this one is emitter, this one is collector. Now, if I build a circuit, if I make a circuit like this, then this part behaves like a resistor. And in this configuration, it is a resistor with very high resistance. Because I mean, actually, we can even recognize why. Yeah, because if I cut transistor into halves, I can see that the top half, well, is a diode. And P-type is on this side and N-type is on this side. So since potential here is higher, so the top diode is reverse biased, and bottom part is also a diode which is forward biased. Well, but I have one diode. I mean, the two diodes are connected in series. One has infinite resistance, one has low resistance. Equivalent resistance of elements in series is equal to the sum of equivalent resistances, so it's infinite. Now let's say that even if I reverse the polarity over here, it will always have high resistance. However, in a transistor, that resistance, this resistance of the capacitor actually can be controlled depending on this what we do with the base. If we connect another source over there and inject, I mean, now this junction over here is forward bias. Current will start to flow and inject charge carriers into that P-type region, which will automatically drop resistance of the resistor between collector and emitter. So the transistor begins to conduct current in this direction. So current on the diagram, if we provide current through the base, much bigger current will start to flow through the collector. I will make a plot of it. A properly biased NPN transistor should have higher potential at the collector, lower potential at the emitter, and potential of the base has to be slight. I mean, if potential of the base is sufficiently low, resistance of the transistor is high. If I increase potential of the base sufficiently, it will have to be higher than potential at the emitter. Transistor conducts. All right. And if I plot current flowing through the collector current versus base current, this is going to be the plot. If base current is 0, collector current is 0. If base current increases, collector current increases by a large factor. typically in transistors, collector, I mean, when it is in operational mode, increasing base current by 1 milliampere will increase, or let's say microampere. Well, let's say increasing base current will cause that collector current will increase 100 to 10,000 times more. It's a tiny change in the base current changes collector current by a lot. And and actually this part of the characteristic of the transistor is used in devices which are called amplifiers. I was hoping to talk about it today, but I see that I won't be able to. I also built an amplifier over there. Now, in computers, we actually use this part of the operation of the transistor. Well, because we toggle between this point and this point. So either the transistor is on or off. You probably heard, and particularly those of you who study computer science, that you had either transistors either on or off. On means that the collector current is maximum. Transistor is practically behaving like a piece of wire here. This part is like a piece of wire. Or it is turned off, so these 2 points are disconnected. You could also hear that phrase that the transistor behaves like a current-controlled switch. Yeah, it either transmits or not. However, in the amplifier, it isn't a switch. In a logical circuit, it is a switch. All right, so this will be all for today. Thank you very much, and we'll return to this subject on Monday.